Welcome back to Multigrid Methods. Last time we were talking about the subspace or successive subspace optimization method, SSO. We outlined this procedure for proving the convergence of this method by showing what was called an upper bound for corrections and a lower bound for corrections. And we concluded the lecture last time on Tuesday with the proof that the upper bound on corrections holds, namely, well, let's see. So the thing that we wanted to prove is this estimate here. And the lower bound on corrections was much easier. It was very straightforward. The only thing that we really used in that case was we used the orthogonalization, but then we also used the strong convexity statement. And that was basically it. The upper bound on corrections uses a lot more stuff. So it involves, first of all, a lemma from last time, from the last chapter 10/11 of this form. And it also used very importantly, it also used the stability of the subspace corrections or the subspace decomposition. And it also used, very importantly, this strengthened Cauchy-Schwarz inequality, in particular right here. So let's see, that actually should be, this is a typo. It should be an inequality at this stage here. So that should be less than or equal, right? So the application of the strengthened Cauchy-Schwarz inequality tells us that this object here, whatever this strange object is less than some constant times the product of these two. And then finally, to finish this off, we use the stability of the subspace decomposition. So this shows that everything comes together to prove the upper bound on these corrections, ultimately giving us this estimate. Remember, we needed a lower bound on corrections and an upper bound on corrections. We put these two things together with our little lemma, and that allows us to conclude the convergence. And so, in fact, that's basically the very next result. We use that lemma now that we know that we have an upper bound on corrections and a lower bound on corrections. The lower bound comes with this constant mu over 2, so it only involves the constant from the strong convexity. The upper bound has the strong convexity constant, but it also has the two constants associated to the strengthened Cauchy-Schwarz and the stability constant. So this one, as I recall, was the stability constant, and this one was the strengthened Cauchy-Schwarz. Once I have, or I know that I have these upper bounds the upper bound on corrections, the lower bound on corrections, then we use our little lemma to put these things together. We find that we have a convergence, and the convergence rate rho is completely, it's first of all, the convergence rate is strictly greater than 0 and strictly less than 1, which is what we required. And notice that we see this obviously from this contraction right here. If I have these two constants appearing on the top and bottom, and I have another constant on the bottom in this additive sense, then of course this has to be a number which is greater than 0 and strictly less than 1. So this is our contraction rate or convergence rate. Once we have this convergence rate in the energy, we have this energy contraction, then we can prove that we also have a norm, a contraction in norm. So we discussed how that works as well. All right, so this is the SSO method. There are pluses to this method, and there are downsides to this method, which we want to discuss shortly. The big downside is that it's not necessarily super efficient. The plus side is it's about the smallest contraction rate that we can possibly get within this framework that we're using, this subspace decomposition framework. It's the smallest contraction constant that we can get for the energy. And so in that sense, it's the fastest, but in that sense, it's kind of the most efficient. The what makes this method not necessarily usable is that it turns out in implementation, it's very expensive, very costly. So there are things that we can do to lower this cost. And so that's kind of the next step. So what can we replace this with? How can we generalize this SSO method to get something which gives us a faster method, but it gives us a faster, more efficient method at the price of the contraction factor is going to go up a little bit. So it won't be as small as this. But remember, this is a small contraction factor with a relatively high cost. It's a little bit like saying, okay, well, suppose I want to come up with a really good iterative method for solving AX equals B. So, or AX equals F. What's a really good, fast iterative method that contracts virtually infinitely fast? Well, I could simply say, here's the iterative method I want to use, A inverse F. Well, the cost is too high. Obviously, this is going to converge in one iteration, but the cost is per hit too high. And there are methods which are very cheap to implement, like your basic Gauss-Seidel method or your basic Jacobi method. Very cheap to implement, but the contraction factor is not so great. It's very close to 1, right? And so there's always this trade-off with something that contracts at a very rapid rate, but may have a high cost. We're trying to balance those two issues, the contraction rate and the cost of implementation. So the next um, the next method that we're going to analyze is one where it strikes a balance between the SSO method and and let's say something um, it strikes a balance between something which has a small contraction rate and something which is cheap to implement. But before we get on to that full description about what that generalized method is, I want to take a brief digression and a brief detour to talk about something called the full approximation storage method. So the FAS method. This is not ultimately the method that we're going to analyze. This is a classical method which has been known in the multigrid community for many, many years. The problem with the method is it's hard to analyze. It doesn't necessarily work globally. And by that, I mean, you may have to have your initial guess be very, very close to the true solution in order to prove convergence. So it's what we call a very local method, or the convergence proof is a very local proof. Um, but it's a method that's well known in the community and something that works quite well much of the time. So the idea is we want to come up with a kind of method which generalizes SSO, but looks a lot like this more classical method called the FAS method, the full approximation storage method. So this method, full approximation storage, I'm going to talk about in this little section here, just in a few short slides, was developed by this guy named Aki Brandt in the late 70s. And I want to put this in sort of a context that we kind of already understand. So I'm going to go back to the context of the finite element method. And so remember what the finite element method was. We had this weak formulation, right? And the idea there was, well, we're going to replace the solution space and we replace the test space with a finite element space. So we're looking for, in this case, let's say in the original PDE version, we're looking for U in H01 that satisfies this weak formulation for all test functions V in H01. And as I said, the way you make this work in the finite element setting is we replace this infinite dimensional space with a finite dimensional finite element subspace. Now, this variational problem can be uh, realized as the Frechet derivative of of an energy. In fact, let me write out what that energy is. So basically, this problem represents the Poisson problem, right? It's the weak formulation or weak version of it. But I can come up with an energy where this variational form the um, is the Euler equation for this weak form. So it is precisely 1/2 gradient u, or nabla u squared, minus u times f. So that's the energy. If I take the variational derivative, or if I take a variation of this, or in other words, if I calculate the Frechet derivative of this, then the Frechet derivative works out to be dEu equals, well, the way I can write it is, it's not so easy to write it in that way. Let's write it like this. The Frechet derivative writes as, it's going to be A uv minus f of v L2, right? And we want to set that equal to 0. And of course, it has to hold for all v in H01. This allows us to realize that essentially this PDE is the Frechet derivative, in some sense, of this energy set equal to 0. Set equal to 0, I have to set it equal to 0 in order to get the f on to the left, or to the right-hand side. Right. Okay, so the nice thing about this problem is it's got a quadratic energy. And when I take the derivative of that energy, it gives me a linear problem to solve. Okay, the derivative ends up being, or the operator representing the derivative ends up being linear. Okay, right. So of course, then if we want to solve that problem for the finite element space, we do the usual sort of things, right? We introduce a mesh, and then we calculate a conforming finite element space with respect to that mesh, et cetera, et cetera. So essentially what I'm saying is we come up with an energy, we take its Frechet derivative, set that equal to 0, and that's of course exactly equal to our weak form, okay, weak formulation. The only thing is we're doing this over a finite element space rather than over this infinite dimensional space, right? Okay, so now we already have methods for solving this, right? What method should we use? Well, let's use the multigrid method, or maybe something a little bit simpler. Let's use the two-grid method, right? So now, so that's the linear case, but we can generalize this idea a little bit. And the way I'm going to generalize it is, well, let's talk about this two-grid algorithm, but for the case where this linear operator is not necessarily specified. So in the last case, the linear operator that I'm referring to here, LH, would be equal to minus the Laplacian operator. Actually, let's see. Yeah, right. And so, but we can generalize this, right? We can say, well, let's just suppose it's any linear elliptic operator, okay? And so this would be this is kind of like the representation of the Euler equation, or I could say it another way. The Euler equation is represented like this as a kind of operator equation. Okay, right. So how do we want to solve this? Well, we're going to look for the finite dimensional solution from the finite element space that satisfies this equation. How could I think about this equation? Because normally you're thinking about it in the weak form. Well, I could think about this as is this really linear? Well, yeah, I mean, it's just going to be AU equals F, right? So that's the manifestation of that linear operator equation as a matrix problem. And it has exactly this form, right? Okay. So now, of course, the two-grid algorithm is predicated or built upon the following sort of ideas. You're going to do some smoothing, right? And then you're going to use a coarse grid correction. And the coarse grid correction works because we have this thing called an error equation, and the coarse grid correction is an approximation to the error equation, right? But essentially, we're doing smoothing, and then we're using some sort of coarse space to do a coarse grid correction. So, of course, to do the coarse grid correction, we need a version of the finite element space on the coarse grid, right? We call that thing, or we can call that V capital H. Capital H is the coarse grid finite element space, and V sub H is the fine grid finite element space, right? So in that case, usually the story is you have some sort of coarse finite or coarse mesh associated to this. You do a refinement, usually in 2D, by doing what's called a quadrisection, and then of course you get a fine grid, and then finally you have the finite element space is the space of usually piecewise linear functions over that finite element space, right? And so here's the pseudocode for 2Grid. Remember, this is all prehistory, right? So how does this work? Well, it's an iterative algorithm. And you put in the previous guy and you turn the crank and it spits out the new approximation, right? So here's how I'm going to represent this as in pseudocode. So let's take this as the initial guess for our little algorithm, right? We'll call that or rename it V0. Then the next thing I'm going to do is I'm going to smooth using a linear Gauss-Seidel method on the fine grid. And after I do that, I'm going to call that V1. Okay, so that smooth using linear Gauss-Seidel or linear damp Jacobi or Richardson's method, whatever you want to use there, do the smoothing and you get the V1 out. Now, V1 is an approximation to the true solution, maybe not such a great approximation to the true solution. And so, because it's not an exact solution, it has an error and a residual associated to it. So let's calculate the residual for that. Remember, it's supposed to satisfy, the true solution would satisfy LHUH equals FH. And V1 as an approximation of UH doesn't quite satisfy that equation, so it has a residual, and the residual is F minus the linear operator acting on V1. Here's our two-grid method. We take that, and we're going to take the residual, and we're going to push it down to the coarse grid from the fine grid, right? So this arrow is meant to suggest we're pushing this down from the fine grid to the coarse grid, and that operator is, we're going to label here R sub little h. That gives us a residual, a kind of residual, which lives on the coarse grid. And then the next thing we're going to do is, remember this, we solve that coarse grid problem. And in the two-grid algorithm, you solve it exactly, and you get this thing called, we're going to call it SH here. And this SH is the, it's kind of like the coarse grid correction. It's the pre-coarse grid correction in some sense. It's just a solution of that equation. It lives on the coarse grid. To get the coarse grid correction, you have to push it up using a prolongation operator back up to the fine grid, right? And so what we're going to do is use that to correct that previous best guess we had, V1, and we're going to call the updated thing V2, right? So P capital H is the prolongation operator, takes something from VH and pushes it up to the fine grid, V little h. All right, remember pH and RH are usually related to each other through the restriction operator, right? And I failed to mention, what is LH, L capital H? L capital H is a version of the linear operator, but that is realized on the coarse finite element space, right? And usually LH in the previous work that we did was determined by some sort of Galerkin condition. Well, we solve that. We get SH. We push that up to the fine grid. We add it on to the previous best guess we had on the fine grid, and that gives us our updated solution. And then what's the last step of the two-grid algorithm? We smooth that using, let's say, linear Gauss-Seidel or Richardson's method uh, or damp Jacobi, whatever we want to use, and that gives us a smoothed solution. And that V3 is what we're going to call our updated guess UHK plus 1. So that's the linear two-grid algorithm. Now, the big question is, the $50,000 question is, what do you do in the case when the equation that you get out by taking the fresh A derivative is nonlinear? Well, that's a good question. Let's put that on hold for just a second. Why does the linear multigrid method work? Well, remember we said there's a bunch of components which go into that. There's the approximation property, and there's the smoothing property, and then of course you had to have a Galerkin property. Those three ingredients went into the mix. You stirred that up, and it all worked. But really, the reason why it worked is because we had this error residual relationship. So it works like this. If I have an approximate solution WH to my true solution, then if I knew the error between UH and WH, then all I have to do is add on the error to the WH and I get the true solution, right? So that means I don't have to solve the original equation. All I have to do is solve an error equation. But the error equation is entirely equivalent to the original equation, and it has this structure. LE equals RH. LEH equals RH, where RH is F minus, that's a typo there. There should be an H there. Okay, so missing subscript H. Well, this residual is always computable. The thing that is the question is, well, is the error computable? Well, it's no easier or harder than computing the true solution to begin with. That's why it's equivalent. So it's not necessarily going to be easier to do this, but we can see there's a clear equivalence between the error equation and solving the original problem. RH is computable. LH, that might not be as easily gotten. And we can think about, in the two-grid algorithm, this key component here, PHSH, that's the coarse grid correction. That's an approximation for the error function. That's an approximation for EH. And basically everything works because we have this linear equation, or this linear operator, and the error residual equation is completely equivalent to the original thing. All right, now let's answer the question, what do you do when you have a nonlinear operator? So now you think, I'm going to start off with an energy, but when I take the Frechet derivative of that and I look at that operator, the Frechet derivative is an operator. If I get a nonlinear operator or a nonlinear equation coming out as the Frechet derivative, nonlinear operator, then the equation that I ultimately have to solve, it can be related or is characterized as some nonlinear system of equations, right? So instead of solving or needing to solve, this is hammered into us. So remember, whenever we have a linear system, it's always the stiffness matrix that we have to invert, right? We have to solve A, U equals F, right? But now this is no longer what's coming out, because the thing that we get when we take the variational derivative or the Frechet derivative is not something which is linear, but something which is nonlinear. So what that looks like is something a bit like this. So it's going to be a nonlinear system of equations involving U equals to F. Well, we can solve this. It's not a problem. The way we solve this is to use something called Newton's method, for example, right? So we apply Newton's method to solve this system of equations. that's doable. But we want something actually which is going to be a little bit easier to analyze, to put it one way. So the equation we get from, let's suppose, an energy gives us this nonlinear operator when we take the derivative, and therefore a nonlinear equation on a finite element space. Okay, so we have to solve this nonlinear system of equations on the finite element space. And how do we do that? Well, the full approximation storage method, which, as I mentioned earlier, originated in this paper by Brandt in 1977, was designed to overcome the fact that we no longer have an equivalence between the error residual equation and the original equation. It's also an iterative method. You put in the old iterate and you turn the crank and you get out the new iterate. So the first thing you do is save a copy of your input vector or function as V0. And then we're going to smooth that. Well, how do we do smoothing for this nonlinear system? We know how to do linear Gauss-Seidel. Well, it turns out there's something called nonlinear Gauss-Seidel, which works pretty well to smooth the system of equations out. It's a little harder to prove that it converges, but that's kind of one thing that we're going to address with the analysis that we're about to do. Right, so we can still do smoothing as before. Not a huge problem. The problem is when we go to calculate the residual and then the coarse grid correction, there's no real way to do this anymore because we no longer have this equivalence between the original problem and the residual equation. It's a broken equivalence. So to do this, we have to calculate first this thing called, this weird, strange object called the tau perturbation. So the tau perturbation has built into it something which was in the two-grid method, the two-grid part. And so that was this thing where we're projecting, or sorry, we're restricting the residual down to the coarse grid. So that part there is kind of similar. This object here is still called the residual. Okay, and we still have something called the error. It's just not, the error and the residual are no longer related through, so we could still say, okay, you still have something called an error, and you still have something called the residual, but they no longer satisfy an equation which looks like that, where NH is the nonlinear finite element operator. Right, so what do you do in that case? Well, I can still calculate the residual. That's that piece. I can still take the restriction and push that down to the coarse grid, but that doesn't get me enough. I don't have a error residual equation. So I have to calculate this thing called the tau perturbation, and it has one more piece that is not present in the linear multigrid setting. It has this. So this N capital H, this is the coarse grid version of the nonlinear operator. Okay, so that's one thing. What is this thing called? QHV1. QH is a projection operator that pushes this function V1 from the fine grid down to the coarse grid, where I'm able to act on it with this operator N capital H. N capital H, again, that's the coarse grid representation. Maybe it's related to something, is related to the fine grid nonlinear operator through something similar to the Galerkin method, or to the Galerkin condition. But the Galerkin condition doesn't make much sense anymore. Remember, Galerkin condition, that involves something called the wrap condition. A H equals R something, it looks something like this, R H P H. Okay, so in our current notation, that would be the Galerkin condition, but that doesn't really work for nonlinear equations. It only works for linear things. And in this case, specifically matrices. Doesn't work. Okay, so this QH is what's called a projection operator. It's a lot like a restriction operator because it moves information from the fine grid space down to the coarse grid space. But unlike RH, this QH isn't necessarily related to the prolongation operator through transposition. It's a bit different. Okay. Now once we've got this tau perturbation, whatever the heck it is, which is on the in the coarse grid finite element space, I can formulate an equation which looks like this. All right. So this equation, what is this thing? Well, it turns out if I solve this problem up here, if I solve this problem where I have this thing called the tau perturbation, this solution no longer looks like an error. It's more like something which looks like the original, well, the true solution, actually. So what I'm going to do is to calculate something which does look like the coarse grid error, the so-called coarse grid correction. I'm going to take this thing I'm finding here, and I'm going to subtract from it QHV1. This thing, or this object here, QHV1, is what is called the full approximation. The full approximation. And so that's why this method is called the full approximation storage method, is because I have to keep a copy of this guy around in order to carry out my algorithm. I know I already know I have to keep a copy of V1 around because I'm going to have to correct V1. But the new thing called the full approximation is QHV1. That guy lives on the coarse grid. I have to subtract him off of this solution here. Remember, I'm thinking about, so FAS is in the spirit of the two-grid method. I'm thinking about solving this exactly on the coarse grid. Once I have that, I'm going to subtract N capital H minus QHV1. And that function lives in VH, V cap H, and that's going to be the pre-correction. Now everything proceeds in the same fashion as before. I take SH and I'm going to push it to the fine grid. This is called the coarse grid correction here, that PHSH. I add it onto V1, which I had to save, and that gives me V2. And now I'm back up on the fine grid, and so I'm going to do what I did before. I'm going to apply nonlinear Gauss-Seidel or some other smoothing method, and I'm going to get a smooth approximation. And once I get that smooth approximation, I'm going to update my U, I'm going to call V3 UHK plus 1. Okay, well, it's hard for me to justify or explain what is this tau perturbation, but I do want to make a couple of comments. Number one, we're going to justify this when we get into the second slide deck for chapter 2. That's the first thing I want to say about it. Number two, if NH, N cap H, and N little h are linear, then this tau H problem, it's not the residual. So it's not the residual. However, once I form this equation on the coarse grid, that gives me an equation which is exactly analogous to my linear two-grid method. All right. In fact, this SH that I'm going to calculate from doing this little manipulation here is going to be exactly the same as the linear two-grid correction. And this coarse grid correction that I compute here is exactly the same. In other words, when I do this whole process, if everything in sight is linear, then this just becomes the linear two-grid method. So FAS becomes the linear two-grid method. So that's the second takeaway that I have for you. This is going to be justified later and made sense of later. It's a little bit hard to understand what it means now, but the second point is if everything in sight is linear, N cap H and little h, then everything just reduces to the linear two-grid method. So now there are some problems still with FAS. Okay, so it turns out it gives us a method which gives us the possibility of computing um, a subspace optimization. Well, it gives us a method of computing the solution to this optimization problem. In other words, solving this nonlinear system of equations without having to worry about the fact that we've lost the error residual relationship that was so useful to us when we constructed and analyzed the linear two-grid method. So it works, and it turns out is very efficient. So FAS, when it works, actually it has almost the same, or converges with almost the same rapidity as the linear two-grid method, which is kind of remarkable. I don't have an example to show you that, unfortunately, in this set of notes, but I can tell you that from my experience, the FAS method for certain nonlinear equations can be converged just as rapidly as the linear two-grid method, which is quite nice. There are some downsides of that. So it's much converges much more rapidly than, let's say, SSO. It's much cheaper. But I can't, and analyzing why and how it converges is not as easy as proving that the SSO method converges. For one thing, SSO converged globally. It didn't matter what my initial guess was. SSO doesn't care. It uses convexity to show that I'm going to converge no matter what. So the analysis of our FAS method, it turns out, can never be very general, and it can't be global. It has to be very local in nature. So what we want to do now is let's try to think about a way of generalizing FAS and simultaneously generalizing SSO in a way that we can get a method which kind of has the best of both worlds. So it can converge provably like SSO for any energies which are, have these nice properties like strong convexity and the local Lipschitz smoothness, et cetera, et cetera. But it's fast like FAS method. So we want to generalize, and it works very rapidly like FAS, but it still has the convergence theory of something like SSO. So that's kind of where we're going. All right. So in the next slide deck, we're going to generalize the FAS method and SSO with something which has a nice new acronym. But before we do that, I'm going to pause here and I'm going to give you guys a chance to ask some questions if you have any. All right, so second slide deck of chapter 11. So the chapter title is still the same, axiomatic method of subspace corrections. So we've talked about successive subspace optimization. That's a method of subspace corrections. And now we're going to introduce a brand new one, which goes by the title, the Fast Subspace Descent method. Fast Subspace Descent method, which we gave the acronym FASD. I guess you have to borrow FAS and D, Fast Subspace Descent method. Okay, so we like that one because the acronym has FAS in it, but it adds a new thing here. It's not quite FAS, it's not quite SSO, it's somewhere in the middle, and hopefully has nice properties of both. Now, for the SSO method, let's rewind a little bit and remind ourselves what we had to do there. So actually, that one was kind of easy, right? So what you did was in that method, you built a bunch of these energy sections. And so what? So we started off by saying we said V0 is equal to U K, right? And then so And then we formulated something called we got inside of a loop. So we said do, or no, I guess for is the usual thing now. For I equals 1 to n, right? So we formulated this thing called the J section, J I K of W. That was equal to the original energy at the previous step, so that would be VI. I guess I put a K here before. So VIK, and then we're going to add W on. And then what we do is we minimize this energy section over this subspace W. I should have said W is in, it's very easy to state this method. W is in that subspace VI. And then how we update this is we get a correction. EIK was equal to this argmin. Well, it's down here. You minimize this section over this subspace, and that's what you call the the correction. So this has a lot of similarities with multigrid, right? So multigrid, you push things down to a coarse grid, you calculate a correction, then you're going to add that correction onto your current best guess. It's just we're not really separating out the process of doing a smoothing from the coarse grid correction. In fact, we're going to treat everything, the smoothing step and the coarse grid correction step is kind of treated in the same way. Okay, it's treated from the same perspective. And it turns out I can completely do that. I can put everything in the perspective of doing this optimization of my energy, my what's called the ambient energy, over these subspaces, and that can completely characterize my entire algorithm. Okay, my multigrid algorithm. So in the linear case, the thing is my energy turns out to be quadratic. So in the nonlinear case, the energy is not quadratic. Okay. So uh, the way I want you to remember this is for the non-quadratic case, you should be thinking about, you should have a good example in your mind. And I think probably the best one to put in your mind is for the non-quadratic case, we're thinking about solving problems like this. 1/4 x to the fourth plus mu over 2x squared. Okay, so the energy has to be strongly convex, and this is a perfect example of that. And now if you want to add on a right-hand side to this, we could do minus x times f. And so the equation that I'd have to solve in the end is going to be something which is a nonlinear x minus f equals 0. What is that nonlinear thing? In this case, the nonlinear thing is going to be x cubed minus mu or plus mu x minus f, right? So this part here is the nonlinear part. Okay, that's my n. That's the, well, let's see. I'll do it like this instead. There we go. Right? So that's the nonlinear part. Um, so if I want a linear equation to pop out in the end, my E should be quadratic. If it's not quadratic, let's say it's fourth order like this, then I'm going to get a nonlinear equation to solve whenever I set my Frechet derivative equal to 0. So SSO works for this method. And the idea is I'm going to do these successive subspace optimizations over these energy sections. That's the kind of main idea there. Now, the cost, the reason why this gets so darned expensive is that whenever I do this process here, that's expensive because I have to keep referring all the time back to my ambient energy E. So that means even when I go to the coarse grid correction or the coarse grid, the true finite element coarse grid, I'm still referring back to my original energy. And this turns out to be fairly expensive. And I need to try to find a better way of doing this. And the better way of doing this is to define something like a coarse grid operator. And the analog to the coarse grid operator is the so-called coarse energy. All right, so you can think about it like this. On my fine grid, I'm going to have something like the original energy. And on my coarse grid, I'm going to define something new called a coarse energy. And that's going to live only on the coarse finite element space. Okay? So the idea is to introduce something new, something different. And that something different is going to be this coarse grid energy. Now, in the quadratic case, the two are exactly the same. In the quadratic case, the two things are exactly the same, and there's no real difference between the coarse grid energy and the fine grid energy, period, full stop. And so that's what makes the linear multigrid method kind of work so well. In the nonlinear case, that's no longer going to be the true, or no, it's no longer going to be the case, and I am actually going to have to introduce something new at this coarse grid. So that coarse grid energy is the new thing. Well, let's talk a little bit about the procedure that we had in SSO. When I think about this procedure, it's going to naturally give rise to something, to some operators that I hadn't really had to think about previously. Hadn't really had to think about previously. And that's because they were kind of built in to the space, to everything. So in the SSO method, I had to solve at each time I did a subspace optimization, I had to solve something which looked like this. I wrote it like this. Um, yeah, I guess V plus, okay? So the idea here is, well, this guy here, you might be thinking to yourself, maybe this doesn't actually make sense, right? Because this had to work for all W in VI, right? So this is let's see, it's a Frechet derivative of an energy which lives on the full space. So this guy is where does this guy live? This guy lives in V prime. Okay, so that's called the dual space of V. But what about this guy? This little element here lives in VI. How can something from V prime act on VI? Something from VI. It seems like it's incompatible, right? So this is a linear functional which should only act on things in V. Well, the reason why it works is because VI is a subspace of V. So it's actually quite natural. It just works. Okay? Because W is in VI, which is a subspace of V, right? It's a vector subspace of V. Could even be all of V. This really still is acting on something from V, period, full stop. Now, but we are allowed to think about how does this guy actually get into V? How does this guy get into V? And what about this guy here, right? Well, that is supposed to be an element also from VI. That's going to be the solution of this equation. It's actually the solution of the energy section problem. What about this guy? This guy here was just something else in the space, okay? We can say, okay, well, that guy is from V. It was something that got corrected in the previous space V, the previous VI minus 1, but now it should live in the parent space V. But this guy definitely lives in VI. Well, I can think about something called the injection operator, or the belonging operator, I guess. Injection simply means that it's an operation that's basically built in via inclusion. So we know that this is a subspace of that. So this inclusion operator simply pushes things from Vi to V by virtue of the fact that this is a subspace of V. Okay, I don't have to do really anything. But it is sometimes useful to think about adding that operator back in there. All right. So it's a little bit funny though. It's a little bit like saying that R is a vector subspace of R2. Is that true? Is that true? Actually, it's not really true. It's kind of true, kind of not true, right? So R is a subspace of R2. What do we really mean by that? Well, there's the real line, and here's R2. So is R a subspace of R2? Yeah, but what we really mean is this is the space spanned by the vector E1 hat, okay? So what we really mean by this is a subspace of that. So we really mean, well, actually you take a number from R and you're going to puff it up, right? So really I'm saying I take a number X and I'm going to puff it up to R2 by just padding it with a 0. That's an inclusion operation. That's an inclusion operation. Okay? Um, in some cases, I really don't have to do anything, but some cases it's nice to think about having done something. And in this case, I'm padding this with a 0. That's what inclusion operations do. So even though I'm solving this like this, and this all makes perfect sense because of embeddings or inclusions, it's nice to put that inclusion operator in there sometimes. So I'm going to add this V here to I. Why am I doing that? Well, because I'm thinking about this guy as being in V, and so I'm going to push this little v here from Vi up to V using the inclusion operator.
I have a
What
quick
about this guy?
question.
Yeah.
So I try to make sense of the notation. So for example, in functional analysis, I
Hmm.
have a function in H1, but later I actually have a operation that only acts on functions in L2, and then but we sorry, I flip it L2, but no. Yeah.
You
So
had
I
it
have a
right the
function.
first time.
Yeah,
Yeah.
exactly. Yeah, I have a function in H1, but now I have an operation in L2. So
Correct.
I need to kind of naturally like rename it from H1 to L2. So is that the same concept of inclusion
Yeah.
operator
And
here?
well, really, truly, anytime I have vector subspaces, right, then I can really think about the inclusion operation. Uh,
Hmm.
in that case, you're just moving a function to the same function. And so there's nothing really to be done there.
Yeah,
I
you
think
just
this,
rename it and
correct. I think this example of R2 is really the best that I can think of.
okay.
Or how do I think about R as being a subspace of R3 or Rn, right? Well, R is just one of these axes. And I think about adding zeros in order to put that into R2 or R3 or Rn. So there I actually have to do something. But in the example you mentioned, there's nothing really to do. There's nothing really to do. Um, but you can still think about it as being an inclusion operation. It's just sometimes there's really nothing to do and sometimes there's something to do, right? But now this is really not true anyway. So when I make a statement like that, that's not really true, right? Because this is a one-dimensional thing and this is a two-dimensional thing. How could I think about this being a subspace of that? I can't even add those things together. I can't think about them, right? This is a scalar and this is a vector of two scalars. So, right? This doesn't make any sense actually. But we know how it makes sense, right? What we really mean is to say the space spanned by E1, right, that's really what we mean, right? Or we could say the space spanned by E2 is a subset and subspace of R2. That's really what we mean. But here, yeah, in the case that you gave, There's not really anything to do. And a lot of times there's nothing to do at all. But now, here, let me give you another example. So it all comes back to finite element. I'm going to go a little bit off topic, I guess, here for a second. So how do I represent finite element functions, right? So there's a finite element function with 3 degrees of freedom, right? And I can think about this guy here, right? Where it only has 1 degree of freedom because it's piecewise linear and piecewise linear, as still being in this subspace that has 3 degrees of freedom, right? Right. So we might say that this is in V0 and this one is in V1, right? According to our previous work. Now, I might just represent this. I might say, okay, all functions in there, that's just 1 degree of freedom. I could just represent that by R, right? And what about this guy? I could represent that by R3 because it's got 3 degrees of freedom. And that's exactly how I do it. So now when I represent this in the computer, all right? So when I represent this as a two finite element functions in the computer, I'm really only saving this degree of freedom, right? The single degree of freedom. Now, what happens if I want to add these two functions together? This function, let's say the function in blue, I'm going to make it blue. How do I add the function in blue to this function in purple? Right? Well, you might say to yourself, the function in purple and then the function in blue are really in the same space. They're just function spaces. Both of them live in V1. So this guy's in V0, but it's also in V1 by inclusion, right? But when I really add them together in the computer, I actually have to do something with this single degree of freedom. I have to pad it with some numbers, not 0, right? I'm gonna pad it by adding 1/2 of this degree of freedom plus that one. And I'm gonna, as my third degree of freedom, I'm gonna take 1/2 of this and that number, and that gives that value. And now I can add the two things together. And so in the case of storing finite element functions, this inclusion operation, you actually have to do something. You really have to do puff this function up in order to add it onto this function here. Okay. So that's kind of what I'm thinking. All right, now, now this inclusion operation, right? That's all very natural. Just VI as a subset, subspace of V, so everything makes sense. But what about this? I'm going to think about the transpose of this operation. Well, how the heck do you think about transposes? Well, it turns out in the functional analytics setting, there is a way of thinking about doing a transpose of this operation, right? And I can call Ri the transpose of the inclusion operation Ri, Ri is equal to the transpose of the inclusion operation. And that guy takes objects from Vi prime and it moves them into V prime, which is the dual space on the parent space of V, into the dual space of Vi. How does that work? How does that work? Well, it turns out with this dual pairing, this guy can move over here the same way that a transpose moves over in this typical Euclidean inner product setting. Okay, so this pairing here, what is that? That's a pairing between V prime and V, right? Dual space of V and just objects in V. So is that an object in V? Yeah, I pushed it from Vi up to V. What about this guy? Yeah, we already said that that's in V prime. Now, to be in V prime, it's going to be evaluated at a point in V. Is this point in V? Yeah, no problem. This guy is being moved from V I to VI, or sorry, VI to V, and this was already in V, everything looks good. Now, the way I'm going to define this operation, okay, this is actually how I'm defining this operation, is I'm just going to move this guy over. When I move it over, I'm going to call it the restriction. Okay, the restriction. So now I'm going to interpret this as being in, okay, so this guy is something that was in V prime. I'm now going to interpret it as something that's VI prime. And that thing is in VI prime. That's what I'm calling the restriction of my functional. So this guy now is interpreted as something being in VI prime. No problem. And it's got to act on something in VI. Well, that guy was originally in VI, so no problem again there. All right. So now, why didn't we write this stuff before? Well, the reason we didn't have to write it before is because this is all just kind of bookkeeping. It's all just, we're not really adding any new content. But what we need to recognize is, well, first of all, that these operations exist. The other thing I want you to recognize is when I'm doing SSO, I'm constantly referring back to the original parent space or ambient space energy. And this guy, constant referral to this on subspaces becomes expensive. And so this is something that I want to make less expensive by introducing, instead of having something like this, I want to have an energy which already just lives the on the subspace. In other words, so that when I take its derivative is already in that subspace. So the way I can do this is just by thinking about, okay, well, I could have an energy to begin with, which just acts on VI. So that when I take its derivative, that lives DEI. When I evaluate it at that some point, let's call it V, this lives in VI prime directly. Okay? That turns out to be something which can be fairly inexpensive because this guy is not a high dimensional object to begin with. This is already pushed down to this lower dimensional subspace. Okay, so that might give us an opportunity for designing an algorithm which is somewhat cheaper. All right, so this is the expensive part because V is in VI, but I still have to keep referring back to this fine grid energy. This could be expensive to deal with. All right, so now the way we're going to get around this is using an idea of the FAS method. So again, I'm not going to be able to fully justify it in this setting. I did say it's going to be justified in the second slide deck. It is, and somewhere right around here, which we're not going to get to today, we are going to get to that on Tuesday, our last class. We'll talk about why the tau perturbation is important and why having something which looks like the FAS method or the FAS process is important. But we're going to, again, we want to do some sort of generalization as like somewhere between SSO and FAS, which has like, kind of like the best of both worlds. Okay, so what we need to do is instead of using the original energy in this calculation, where was that? Okay, instead of using the original energy there, we're going to, on every subspace, we're going to define a local energy. And this is like having the coarse grid operator, actually. And that's going to make things a lot less expensive. Now, we need a way of moving objects from the parent space or the ambient space to the subspaces. And we need an operation that does this, which is not necessarily the same as the restriction operation. In fact, it doesn't actually make sense because now we see that the restriction operator And this setting is actually an operator on functionals. So it doesn't even kind of work here. So we have to introduce something called a projection operator. Well, what kind of operator is the projection operator? It's something that we've met before. The L2 projection, for example, is a projection operator. We need something that when we move it, an object from the fine level space down to the coarse level space, does so in a projection manner. So what do we mean by a projection manner? Well, if so if um, so if W is already in VI, then QI W, probably should have written VI, is just equal to W back, right? If it's already in the correct subspace, then taking the projection of that object just gives the same thing back. That's what a projection operator does. So we need, in our new method that we're about to describe on the next page, we need subspace energies and we need these so-called projection operations, okay, or operators. So with that, I'm able to fully define the FASD method, and I'm just going to warn you right away, it's going to be fairly complicated. Found a typo here. It's a little bit complicated precisely because it is something in between SSO, which was something very simple to state, and FAS, which was kind of difficult because it introduced this new weird object called the tau perturbation. Okay. So bear with me as I try to explain all of these pieces. So FASD is an iterative method, as FAS is an iterative method in all the methods that we've talked about. And it's defined as follows. So we're going to assume we have a bunch of course, we know we have our standard energy that satisfies our basic assumptions. And this should say that what does it satisfy? It U is the unique solution to D E U, and I think I read it as W equals 0 for all W in V. So it's the minimizer, right? And therefore it satisfies the Euler equation. So that's what U is. So we're going to compute a sequence of approximations that hopefully converges to U. Now, what we need in addition to the E, which satisfies a certain nice properties, is we need to have these Frechet differentiable subspace energies, and we need to have projections. That's the only new two features that we need for this new method, which is called the FASD method. As before, we're going to copy over the current iterate into something called V0, and now we're going to compute a bunch of corrections, right? So the corrections ultimately should be something that we're going to add on to VI minus 1K to get VIK. That's how these corrections all work. The only thing is, how do you compute those corrections? Well, we're no longer going to call these corrections EI, we're going to call them epsilon IK. So that's the first thing we want to do. Tip you off to the fact that these things are different than in the SSO case. We're still going to compute, like in the FAS method, something called the tau perturbation. Well, first of all, you might complain and say, this looks nothing like the tau perturbation that you introduced for the FAS method. It is exactly the same, it turns out. It's just written in terms of, instead of nonlinear operators, it's written in terms of the derivatives of energies. Okay, derivatives of energies rather than nonlinear operators. All right. Otherwise, it's going to be exactly the same. So the first thing we're going to do is we're going to remember this thing is called the full approximation, and it's still called the full approximation here. We take whatever we had currently as our best guess. This is like the thing get after smoothing in the FAS method, and we're going to push it from the fine grid down to the coarse grid. So that's like pushing it from the space V into VI. And that gives us this thing called psi k. That goes in previously when we computed the tau perturbation, it went in as the operator or the argument for the coarse grid nonlinear operator. Now it's going to go into the argument for the derivative of the coarse grid energy EI. This is still like something which looks like, well, actually the residual is going to be minus the derivative of the of the um, of the energy evaluated at the previous best guess. And now what I have to do is this is an object in VI prime, right? Because EI is an object in V acting on VI, so its derivative is in the dual space of VI, what we call VI prime. So this RI just represents the pushing of the derivative of this object, which is in V prime, into VI prime. That's what a restriction operation does in this energy setting. So this tau perturbation doesn't look like the previous tau perturbation, but it is entirely the same. All right, next thing we're going to do is solve an equation which looks like the coarse grid version of the correction equation we solved with the FAS method. And to save time, I'm just going to run through this, and we're going to come back to this at the beginning next time. Once we solve that, we're going to compute something in the past. This was the coarse grid correction, but now it's just going to give us what's called a search direction. So it has the same structure as before. You take the solution of this equation and you're going to subtract from it the full approximation. Solution minus full approximation. Before that was our coarse grid correction. Now it's simply going to give us a search direction. That search direction is in VI, and what we're going to do is we're going to use that as a direction in which to look for a solution. So we're going to minimize along this direction, this energy. This is our previous best guess. We're going to minimize along that. So this is an energy section, precisely an energy section. But now we're only solving a truly one-dimensional problem because this search direction is fixed and alpha is free. All right, so this truly is just one dimension, a one-dimensional problem. So we're looking for the arg0 of this equation. Okay, this is just how do you solve a minimization problem? You take the derivative set equal to 0. Okay, so we're going to call that the arg0. So we're looking for alpha which satisfies this equation along this search direction space. Once we get that alpha, then we're going to multiply that solution onto the search direction space, or the search direction. Okay, that guy is fixed. Search direction is fixed. Alpha I is now known. That's what is going to give us the subspace correction. We add that onto VI minus 1K. That gives us a VIK. And finally, so we do this over all subspaces. And then finally, we end on the nth subspace, and that gives us our final update to UK plus 1. So this is the algorithm we call FASD, Fast Subspace Descent method. It generalizes SSO and it generalizes FAS method. We're going to show that this guy converges with a pretty decent convergence rate, something not quite as good as SSO, but it's still going to give us what's called a global convergence. And the other nice thing about this is that it has some of the nice aspects of FAS in that it's actually fairly inexpensive to compute. So I'm going to stop there. I appreciate the extra few minutes, and I will take your questions.